Since we've lost the class due to snow this morning and the 2-hour delay, we're going to finish up this section on exponential functions with a look at 2 examples involving money and the compounding effect of interest when either you borrow money or you are fortunate enough to invest money. So there are 2 formulas that we're going to be using to do this. Formula 1 is the one that we will use when the compounding period is twice a year or monthly or daily, anything other than continuously. Formula 2 is going to be the formula that we use when the compounding is going on continuously. Let's take a look at the first example. This is from the handout that I gave you in class the other day. I'm not using it because the font is too small to show up on the video. But this example talks about $10,000. Should anybody be so lucky to win the lottery and get $10,000 to invest, 8% for 5 years. Oh, by the way, nobody gets 8% anymore. This example is from an older edition of the text. Just a heads up, if somebody were to offer you 8% on your money, it's illegal, or they're going to scam you and you're not going to get any of your money back, interest or principal. Today the rates are much, much lower than this. So we're going to look at this when we have 2 different scenarios. The first one is the compounding period is quarterly, and the other scenario is going to be when the compounding is continuous. Let me spell that right. So we're going to be using both of these formulas in this one example. Taking a look at the first one, quarterly, A is going to be the amount, that's the amount of money we get at the end of the period. So either what we're going to have to pay back or we're going to get with interest. P is our principal. So in this case, P is $10,000. And now our formula says we have 1 plus our interest rate. Our interest rate is 8%. However, very, very important, when we use interest rates in these problems, we have to write it in decimal form. So in this case, we're going to use this 0.08. Should we use 8%, our information is going to be incorrect, and either we're not going to get the right amount of money back, should we be the ones figuring out how much money we earn, or we're going to be paying back the wrong amount. So we have our interest rate of 0.08, that's in our numerator here. And now this gets divided by n, which is the number of compounding periods we're talking about. In this scenario, because we are looking at interest being compounded quarterly, the n is going to be 4. You can remember there's 4 quarters in a dollar. Then we close our parentheses according to our formula. And now in our exponent, we have n times t, n being the number of compounding periods, and t being the time in years. So in this case, we're looking at 5 years. So here's plugging in the information to our formula. Continuing on with the calculation, 0.08 divided by 4 is 0.02. So we have 1.02. Obviously here you could put all this into your calculator in one string. I'm breaking down the calculation so that people can follow along where these numbers are will be coming from. And then in our exponent, 4 times 5 is 20. So now in our calculator we would take 1.02, raise it to the power of 20 and multiply it by 10,000. And we get the answer of 14, let me put my glasses on so I don't read this incorrectly, $14,859.47. So that's the return that we would get with the quarterly compounding. Now, taking a look at continuous compounding, we're going to be using this formula here. So again, it's A that we're looking for. P here is the same 10,000 that we had from the first example. And now here with continuous compounding, our base is E. So we have E, and now we have RT. So the exponent here is slightly different. Instead of being NT, it's RT. So it's our 0.08, our interest rate, times RT, which is 5. So this gives us $10,000, and then multiplying 0.08 by 5, we get 0.4. Again, through the magic of calculators, e to the 0.4 power multiplied by $10,000, and that gives us $14,918.25. So there is a difference in the two returns, but it's not a dramatic difference as far as I'm concerned. 14,000 is the same. 918, 859, yeah, it's more. But the truth is, I would have thought with continuous compounding, which means it's always going on, versus calculated 4 times a year, this difference would be more dramatic. Now, moving on to the next example that we have on this sheet. In this particular case, we are told that we have $60,000. So our P is, oops, not 60, $6,000. We're not so rich in this one. Our T is going to be 4. We're looking at 4 years now. And now we have two interest rates. We have an R of 8.25%, and that's going to be compounded quarterly. So N is going to be equal to 4. Then we have another R, which is 8.3%. And that compounding is semi-annually, twice a year, so our N is going to be 2. So again, let's take a look at our formula here. Because we have compounding periods other than continuously, this is the formula we're going to use. And now we have here our 6,000, the one from our formula. And let's do this, 8.25. So it's going to be plus 0.0825 divided by 4, because the compounding period is 4 times a year. And then our numerator, we have compounding period of 4 times 4 years. So that looks kind of redundant, 4 and 4, but it's because we have 4 years and 4 compounding periods. So it is the same 4. So 6,000. And now over here, when we divide 0.0825 by 4 and add that to 1, we get 0.020625. Obviously, that's a lot of decimal places. You wouldn't, in your calculator, would just handle it. But again, I want you to be able to see how these calculations would occur. And 4 times 4 is 16. When we finish up this multiplication, we get the amount of $8,317.84. So quite a bit more from our original 6,000. Now, let's take a look at what happens under the other scenario. Again, our $6,000 P to start with, that hasn't changed. But what has changed now is our interest rate is 8.3%. Again, we got to write that in decimal form. And now we're going to be dividing that by 2, since our compounding period is 2. Up in the numerator, our compounding period is 2, not the numerator, the exponent. So we have 2, and then our T, the years, is still the same 4 that we had originally. So we have our 6,000, 0.83 divided by 2. I'm going to round here. So we have 1 point, and when we do that division, 0.415, and 2 times 4 is 8. So our exponent is now 8. Lastly, we 1.0415 to the 8th power, multiply that by 6,000, and we get the amount of $8,306.64. So comparing the two amounts here, we can see that this would be the better deal. The slightly smaller interest rate, however, because it does compound 4 times a year versus only twice a year, this would be the better investment.